evening. Thank you so much for coming to PolyU late at night. Um, I can see that we've got a nice audience with very diverse backgrounds. Um, and I'm very glad to be here, to be with you. And I know that some of you are joining us online as well. Thank you so much. Okay, so today's lecture, I'm going to share with you something related to neuroimaging. Okay, so we try to use some methods to look at our brain, some imaging methods. Okay, because of the diverse background of the audience here, so somehow it is a bit tricky for me to kind of decide on what exactly that I should tell you. So some of the uh, materials could be quite elementary. So if you are already an expert, please bear with me. Um, But I hope that, well, I could tell you something that is quite conventional and also tell you something about some new directions about how we can use neuroimaging techniques to inform mental health. Okay. Okay, ready? Yeah. Okay, so let's begin. Okay, here in PolyU, we do have some medical imaging equipment. Okay, so across the different modalities of neuroimaging. So here I'm showing you 4 examples. Okay, let me try and see if my pointer works. Okay, here on the top left hand corner, we've got MRI, magnetic resonance imaging. We also have X-ray here on the top right, CT, ultrasound. Okay, so these are 4 examples where we can try and image our brain, take a picture of our brain, okay? Of course, you can't use your mobile phone or camera to, well, take a picture of the brain from a healthy person or a patient, but then you can use these equipments. I would say that nowadays, MRI is, well, one of the most popular methods for us to take pictures of the brain because it has some advantage. The picture taken from MRI is clear, so you can take a good picture of the brain. And also, it is non-invasive. That means that you do no harm to the brain or to the body tissue. Compared to X-ray and CT, of course, well, you probably know that they involve radioactive substances, right? So you would want to minimize your exposure to X-ray, radioactive substances, right? So MRI is quite nice in this sense. Okay, so because it is non-invasive, it involves very high magnetic field. I'll tell you more later on. But this is basically safe as long as you follow safety protocols. Ultrasound has caught some attention. Okay, of course. Well, for example, for ladies, if you've got experience pregnant before, you know that well, using ultrasound you can take pictures of the fetus, right? And we can use ultrasound to take pictures of the brain as well. Although it's kind of tricky, the pictures quality is not as good. So it's still developing. Some it's people are still trying to look for ways to use ultrasound to visualize the brain. Okay, I would focus primarily on MRI. Well, obviously because this is my interest, but not because this is selfish interest, but also that it is something that is, as I said, quite new, quite emerging in different ways. Okay, so let me give you some brief ideas about it. MRI, magnetic resonance imaging. That means that you need a magnet. Okay, it involves a very strong magnet typically. Okay, how strong? How strong is the magnet? Typically, it is 1.5 to 7 Tesla strong. Okay, uh, Tesla, you might think of the company, right? Here we are talking about Tesla in terms of magnetic field strength. Okay, not the electrical vehicle. Okay, not that. But we're talking about electric field strength. Okay, give you some idea about this field strength. Uh, on Earth, we are always experiencing magnetic field because of the Earth, right? And that's why you can take a bar magnet and then it can point you direction, where it's north, where it's south. Okay, so the Earth's magnetic field strength is very weak, 0.00005 Tesla strong. Okay, if you go to a stationary store, get a bar magnet, it would be something like 0.01 to 0.1 Tesla strong. Okay, um, if you go to some well, this disposals of vehicles, they sometimes might use magnets to lift up vehicles, and those magnets are 1 Tesla strong roughly. Okay, so 1 Tesla is enough for lifting up a vehicle. So we're talking about 1.5 to 7 Tesla for most scanners, MRI scanners that we have in hospitals or in university settings. Okay, so this is a picture of a typical MRI scanner, and this is a typical picture taken by a scanner. All right, as I said, well, it's popular because it helps us to take good pictures, clear pictures. And why do we need that? Because, well, obviously, sometimes if for medical doctors, they want to look at abnormal structures in the brain. Okay, sometimes the structures are quite small, and then you need good cameras or you need good imaging equipment to visualize that, and that's why you want to have good spatial resolution, and that can be offered by an MRI scanner. And it is non-invasive. You might be worried, oh, would there be any problem if I get exposed to a very strong magnetic field? And the answer so far is no problem, okay? This type of technology has been around for roughly 50 years or so. And there isn't really any reports of health issues related to exposure of high magnetic field. Okay, of course there can be accidents. For example, well, somebody might have mistakenly taken some metal objects, and that might be attracted by the strong magnet and cause damage. That could happen. But apart from these kind of unintentional mistakes, exposed to strong magnetic field is so far safe, as the medical field has realized. Expensive piece of equipment, probably you might know, if you've got experience for whatever reason, getting scanned by the MRI scanner, they charge you for a certain price. Maybe half of it or most of it would go to the medical doctor's pocket, but all it would be the expense of the MRI scanner itself as well. Okay, so expensive piece of equipment. Okay, I want to play you a video about an MRI scanner because I think, well, just listening to me is too boring, but I think it's better for us to have a look at the MRI scanner. I've got two choices for you. One is a more interesting one, which shows you MRI facility in general, in a relatively cute way. The second one is, well, honestly, a boring one, showing you the MRI facility in PolyU. Which one would you like? The interesting one. Okay, good. Okay, great. Let me show you.
Now, 3 turns to the left. A little more. A little more. Hey, Jameer, what you doing? Hey, Jenny, you scared me. Ooh, Sorry. Is that a hand mixer? What you working on? Only the coolest invention ever. It's a camera that can take pictures of what's inside people's bodies, even their bones and brain and stuff. Pretty cool, huh? Yeah, kinda like an MRI. What? An MRI. There's one right here in Philly over the Children's Hospital of Philadelphia. I had an MRI last year when I fell off my bike and bumped my head. I wasn't wearing my helmet. I'll never do that again. I remember my MRI like it was yesterday. I went to my doctor after I bumped my head. He said to get an MRI just to be safe, so he went to CHOP. Then I met the MRI technologist, Brian, who'd be taking my pictures. He was way cool and so nice.
Hey, Jenny, we're all set up. You ready to go?
Mom waited for me in the waiting room. I told her not to worry, but you know how moms are. Brian showed me the control room. Control room? Like on a starship? Kind of. Anyway, there's all these really cool computers that show pictures taken from the MRI. There's even a metal detector. What's that for? Well, there's a magnet inside the MRI camera that helps to take the pictures. Really high-tech stuff. So you have to make sure you take off any metal objects on your body, like earrings and stuff. Cool! I know, right? Well, then we went into the room with the MRI camera. This thing was huge! I had to climb up and lay down on this bed, which slides into a tunnel. Brian told me it was important for me to lie still, so the pictures won't come out blurry. Because the bed moved, I had to wear a seatbelt to keep me safe. Oh, and there were these cushions for my head and this thing called a coil that helps the camera focus on what body part it's taking pictures of. Mine kind of looked like a football helmet. Football helmet? Follow me, would ya? The machine makes some strange noises and they get a little loud. So they give you earplugs. It sort of sounds like you're at a construction site. Wow, were you scared being alone in that thing? Nah, because you're not really alone. The technologist can see you the whole time through the window in the control room. You can even talk to each other through microphones set up in the camera.
Hey, you're doing great, Jenny.
But it's really important to be as still as you can so they can get the clearest pictures they can. I just closed my eyes and imagined myself on a float in the clear blue waters. Like on a vacation. Wow, that sounds really cool. I guess I've gotta think of a new invention.
Junior, honey, have you seen my hand mixer?
Do you want to ride bikes? Sure, and I even got my helmet.
Okay, so that's the MRI scanner. I know it was for kids, but actually it was quite nicely made such that it tells us some details about MRI. For example, how the setting looks like, and also some safety precautions, like whether or not the patients were taking any metals to the scanner. If they do, that would be extremely dangerous. Sometimes we have metal detectors to make sure that they don't carry anything that is metallic. The scanner environment is very noisy, so that's why you saw that. Well, the kid was given earplugs and to protect the ears, and then they wear something like a helmet. The helmet is for taking pictures of the brain. Okay, so this gives you an overall view of the MRI scanner. Okay. So as I said, as long as you've got some experience being scanned before or witnessed somebody being scanned before, you probably got those ideas already. Sorry. Okay. So I'm going to tell you a bit more on what we can do with the MRI scanner. Okay. I guess most people in this room probably have some ideas that, well, the MRI scanner can help us to take pictures of a body part, okay? And I would call this for the function of looking at structural morphology, okay? looking at structure, looking at the shape of something, okay, to see whether there are any damages or not. Okay, I guess this is kind of general knowledge that we all know. Something that you may not know, okay, if you are not familiar with MRI itself, is that there's something else that can be done using MRI, just the same scanner. But we can use MRI to look at these like chemical compositions, okay, and functional recording, okay. So I'll cover these. I'll tell you a little bit of physics behind that. I hope that won't scare you. I won't go into a lot of details, but just to give you some idea. Okay. Okay. So let's first talk about structural morphology, or most people's understanding of what can be done using MRI. Okay. This is the kind of resolution that can be offered by an MRI scanner. Okay. Um, I guess when I said resolution, many people nowadays they are familiar with taking pictures, right? With your camera, how many pixels your cameras can offer you by a photo, right? So we're talking about something similar, okay? How precise from the body tissue that we can look at it. Okay? Um, the conventional resolution is 1 by 1 by 1 millimeter cube. Okay, you can take a 3D picture from the scanner. Okay, and that is the resolution. Okay, so there are many pixels, right? And each pixel would be 1 millimeter wide. Okay, so that is the resolution. And of course, you can use the scanner to even go further down the resolution. Uh, for example, 0.25 millimeters, still possible. It just takes you extra time to take that picture, but it can offer you an even clearer picture, and this is feasible using MRI. Okay, when we talk about taking pictures, of course, we are talking about different levels of taking pictures. Okay, you can take pictures of using your mobile phone, right? But of course, using a mobile phone, you can't have such a very precise resolution. Then you can also be, well, even more precise about picture resolution. For example, you look at something using a microscope, okay? Looking at cell structures, for example, in the brain. Then that can't be feasible using MRI. So using MRI, we can look at things in, so to speak, a system level. We can't look at things in a microscopic level, but we can look at things at a system level. For example, the shape of the brain, some structures with inside the brain that can still be feasible to look at that. But for example, if you want to look at individual cells inside the brain, then MRI is not a good tool for that. Okay, this is a typical brain scan that you can get from the MRI. You okay, sorry, I forgot to give you a video of that, but you can actually have these many pictures taken using the MRI scanner, taking the picture from the brain slice by slice. Okay, let's say from the bottom to the top. Okay, you get a stack of many pictures, and you combine these many pictures together and reconstruct you a 3D. Okay, so typically, well, due to technical problem today, but typically I will show you a brain rotating here, and this is feasible to have somebody's brain taken and reconstruct it into 3D, and you can, well, have a rotating brain in front of you. Okay, and of course, in medical fields, MRIs are used for diagnosis, right? Let's say whether there's a brain tumor, or whether there's a stroke, or whether there are some abnormalities in the brain structures, then you can use MRI to look at that. I am giving you these two websites where you can find examples of MRI scans. There are many websites available. These are just two examples. Okay, this is one of the websites. So you can find a normal brain using 3D MRI. Let's have a look. So this is a typical MRI scan. I think you all have the slides, and that gives you the link, and you can play around with by yourself. But then here you can, well, browse through, and then you can see a brain in 3D. You can find some structures, for example, some nuclei inside the brain. Let me name a few. For example, down here, we've got a structure called the hippocampus, which I think if you have a little bit of neuroscience knowledge, you know that this is the area for helping us to memorize things. Okay, so that is the memory region. Okay, the hippocampus. You can also easily visualize a cavity inside the brain here, which is called the ventricle. Okay, the ventricle. And as we age, this cavity would enlarge. Okay, because of the shrinking of the brain over the course of aging. And this is quite a obvious marker for aging. So this is the brain of a healthy individual. You can see some other examples. For example, here I can show you, for example, Alzheimer's disease. Okay. Okay, so this is the brain of an Alzheimer's disease patient. You can see that the color is different than the previous picture. Okay, because of different ways of taking the picture, then it will give you slightly different colors. But anyway, the key goal, of course, is to visualize the brain structure, right? Okay, so again, you can find the ventricle. This patient, although it's an Alzheimer's disease patient, the ventricle size is not too big. Normally, you will find even bigger ventricle size. Let me see if I can find another example of that. Yeah. Yeah, this would be quite typical. You see that the ventricle size is much enlarged, yeah, in patients with Alzheimer's disease. Okay, so here I can only have time to show you a few examples, and you can play around with that. Okay, here I'm showing you another example of a patient with tumor inside their brain. Okay, and what I want to show you here is that there are different ways to take pictures of the brain using MRI. Okay, some of them I would just skip the technical term of if you know that they are called T1 scan, T2 scan, but these terms are not important. But the important thing is that it would give you slightly different colors of the brain. The ventricle or the cavity in one scan would look black in color. In the other scan would look white in color. Okay. The take-home message is that these different types of scans, the T1 and T2, whatever they are called, each of them have their own strength of visualizing different tissues. And that is the reason why medical doctors sometimes may need a combination of different scans in order to help them to visualize abnormalities inside the brain. For example, this brain tumor. So that shows you the edema of the tumor, and this is the kind of cancerous part. Okay, and you can see that these two different scans would visualize things in different ways. And perhaps this one on the right, which is the T2 scan, gives you a better contrast in this case. Okay, this is dementia, for example, Alzheimer's disease. As I said, enlarged ventricle is a common problem or common phenomenon. Okay, here I want to show you some reasons why we want to do these structural scans. Okay, of course, identifying damages is one thing, but the other thing is that in research, for research purposes, sometimes we would be able to obtain interesting observations. Okay, such as changes in the brain over the course of training. I'm showing you here this example. Sorry. Um, I lost the full screen button. Here we go. Okay. I'm showing you this example where some researchers try to train people to juggle some balls, 3 balls at a time, 4 balls at a time. Okay. I'm not sure if you have experience learning how to juggle, but it's a very challenging task, right? I can't do it. But these people, they are very dedicated. They try to learn how to juggle. And these researchers try to scan the brain before they receive the training and after that they receive the training. Okay, imagine this skill of juggling need a lot of eye-hand coordination, right? So that means that probably while you are getting trained, inside the brain somewhere that is responsible for eye-hand coordination should become very busy, right? And you need to train up this part of the brain in order to be able to learn this skill. And in fact, it was the case that after some time training, people's region for eye-hand coordination became larger. Okay, and that was found by using these kind of structural scan that we've just mentioned. Okay, so that's why, well, this is one purpose, mostly in research field, why we want to do structural scan. Another purpose would be to look at individual differences. Okay, for example, there's another very famous experiment done in the past with taxi drivers in London. Not sure if you have heard of that. In London, they have a very complex city map, and those who are qualified to be a taxi driver, they need to go through a very difficult test that requires a lot of memorization. Okay, that means that if you are not very good at memory, you probably can't pass that test. Okay, so it's almost like a natural selection process. Okay, and what they found is that these London taxi drivers also have a larger hippocampus that is responsible for memory. Okay, so that can be identified using these structural scans. Okay. All right. Next, I want to share with you another case. Okay, related to how these structural scans can be applied in medical settings. Okay. This is related to a person called Michael. Okay. He was a school teacher. Okay, and then he got married to his wife. Okay, and seems like having a very nice family. Sounds like that he was a nice person, no prior history of criminal or deviant behavior. But like many stories, right? The person began to change. In what way? He became very aggressive with his wife, taking pornography to school. Okay, and then of course being caught. Okay, and then he went to a law court, and Michael had to decide between a prison sentence and a treatment program. Okay, Of course, the story has a little bit of drama in there. Okay, suddenly, Michael went to the emergency room complaining of severe headache. Okay, suddenly, all of a sudden, he had a severe headache, and that's why he got an MRI scan because of his headache. Okay, and that is what was found by the MRI: a tumor growing from the base of somewhere called orbitofrontal cortex. Okay, just a technical term, but the orbitofrontal cortex is a part of the brain right above your eyes. Okay, so your eyeballs are located in a socket in the skull called the orbit. Okay, so it's a space. Okay, that part of the brain that is so close to this cavity holding our eyes is called the orbitofrontal cortex. Okay, what we know about its function is that it's important for our decision making. Okay, when we are making a good choice, we need this part of the brain, and also our inhibition. Okay, to stop ourselves from being impulsive. Okay, we need the orbital frontal cortex. Okay, kids that are very young, perhaps you would agree that they are normally a bit more impulsive. It's also related to underdevelopment of part of the orbital frontal cortex or somewhere else in the prefrontal cortex as well. Okay, so this is important for our impulse control. Okay. Okay, so there's a tumor there in Michael's brain. Okay, and after the tumor was resected, Michael's behavior returned to normal. Okay, so this tumor in the orbital frontal cortex was removed. Michael became normal again, probably because now he would regain the ability to inhibit his behavior or inhibit his impulses. Okay. Okay, you can continue reading the story that Michael suddenly was found having these abnormal behavior again later on, and then he went to a scan, went to have an MRI scan again, and noticed that the tumor was regrown. Okay, so just a case to share with you about the use of MRI. Okay, uh, so far so good. Any questions? Any questions? Yeah, please.
MRI. I mean, if you have tooth implants or if you have some metal plates on your back or anything that's metal inside your body, any group that should avoid?
Yes, very good question. Let's say if for whatever reason that you got a head injury, then you suspect that there's some pieces of metal inside your brain. Okay, then you should avoid doing MRI. Not because the MRI scanner is so strong such that the piece of metal will suck to the MRI scanner itself, but even a small twitch of the piece of metal inside your brain would be extremely dangerous. So that's why this would be one reason. Pacemaker, okay, pacemaker. Those with pacemaker, if they need to undergo an MRI scan, probably the neurologist would communicate with the cardiologist to make sure that the pacemaker maybe stop functioning for a brief while, but after the MRI scan is done, then the functioning of the pacemaker should be resumed. Okay, and that is also the reason why inside an MRI facility, there are some areas where we would put warning signs, because in these areas there are already a little bit of magnetic field that may interfere the functioning of the pacemaker. Okay, so pacemaker is one thing that we are extremely cautious about. Yeah. Okay. Seems that there is another question in Zoom. Okay. Okay, the question is about some developmental disorders, ASD, autism, okay, or ADHD, okay. They are treated as neurodevelopmental disabilities, okay, and then MRI is one possible imaging techniques for better understanding brain abnormalities in these children. Oh, okay. The question is whether there's any age limitation for these children to participate in MRI. Okay. No, they are actually safe to be uh, scanned using MRI. Okay, these children with ASD, autism spectrum disorder, or ADHD. Okay, they are safe to be scanned. The challenge, especially with ADHD, is that we need to keep them still inside the MRI scanner. Okay, I guess you all have experience taking pictures using a mobile phone. Let's say if there's a kid moving around, running, then the picture get blurred, right? Same for MRI. So the challenge would be to keep them still. How do we do that? Okay. All right. Great. Yeah. The MRI scanning environment less noisy. Yes, we can. The question is whether we can make the scanning environment less noisy. Okay. One is, of course, well, the easiest or the low-tech thing to do is to give them earplugs. Okay. But you might think that, well, that might annoy the kids, right? There are some new techniques to make the scanning environment quieter. Okay. Um, even less than half the amount of noise that is being heard. Again, the trouble is that there's always a compromise, right? If those techniques are so good, why don't we always use the quiet mode, right? And the answer is that they are not as good. The pictures are less clear, and that's why still the mainstream is to use those quiet, those noisy approach to scan the brain. Yeah. But very good question. Yeah, thank you. Okay. Okay, let's continue then. Okay, a little bit of physics. I will keep it very brief. Okay. So taking a picture using MRI somehow is like taking pictures using a conventional camera. Okay. For example, on the left, I'm showing you an optical camera. Okay. Of course, now we have smarter cameras from our mobile phone. But there are some commonalities between these devices. Okay. With the conventional camera, it relies on light for us to take a picture. Now, on the right with MRI, it relies on magnetic field. Okay. So some kind of magnetic field is delivered to our body tissue, and that helps the scanner to take pictures. Okay, so that's the general idea. Okay, with a conventional optical camera picture, we talk about picture with pixels, right? Some points that keeps that help us to show the image. And that is also the same case for MRI. We take pictures, we have these pixels, but they are normally in 3D. So we use a different name. We don't call it pixel. We call them a voxel, okay? VOXEL, voxel, okay? Okay, inside the magnetic field, there are inside the MRI scanner, there are three magnetic coils, okay? There are three magnets altogether, three main magnets altogether. Okay, I mentioned earlier on, the magnetic field strength normally is of 3 Tesla strong, okay, 3T. This is just part of the story. This is this field strength of one magnet. But there are some other magnets, so-called the gradient coil, the radio frequency coil, okay? They're doing different things, okay? I'll skip the gradient coil, but the radio frequency coil, what it does is that apart from having a static magnetic field inside the MRI scanner, we have this extra magnet that is occasionally turned on and off, okay? Such that extra magnetic field would be shooting towards the body, okay? In order to let us take pictures, okay? So well, that's why each coil or each magnet is doing different jobs in order to help us to take this picture. Okay, why do we need magnetic field? Okay, because inside our body, there are microscopic or nanoscopic magnets all around us. Okay, what are these magnets? These are actually water molecules. We have a lot of water inside our body, but each water molecule is almost like a magnet, a tiny magnet. Okay, so we need a very strong magnet, the 3T strong magnet, in order to align these tiny water molecule magnets together in a straight line. Okay, so all these tiny water molecules are aligned, so they are not randomly rotating. Okay, and then we also got this RF core that I just mentioned to shoot magnetic field to disrupt the alignment. Okay, so all these will help us to take pictures of the body tissue, for example, the brain. Okay, and I probably will skip this slide, but there's this gradient call thing here. Probably won't cover it, but again, serves some purpose for us to take pictures. Okay, and this is a video showing you how the protons or the water molecules, they are tiny magnets and how they are aligned to the main magnetic field, how they would be disrupted by shooting magnetic field towards them. Okay, and then that's our final product, having this picture of the brain. Okay, so far I've talked about some conventional way of taking pictures. Okay. Apart from that, there are some non-conventional uses of the MRI scanner. Okay. For example, this approach called MRS. Okay. The full name is magnetic resonance spectroscopy. Okay. You use the same machine, but for a different purpose. What it does for us is to help us measure chemical composition inside a part of the body, for example, the brain. Okay. Okay, now after taking, so to speak, a picture using MRS, then we can have a chemical profile of the brain or of a body tissue. Okay. For example, we can measure the composition of something called glutamate or GABA. Okay. These are major chemicals inside our brain for the cells or the neurons to communicate. Okay. There are some other things that can be measured using this technique. For example, creatine, CR, phosphate creatine. These are the chemicals for energy store inside the brain or other parts of the body. Okay, so you can see whether there's abnormalities in these composition. Okay, I would say that the clinical use of this method is still a little limited because, well, it's still a developing technique. Okay, but in the future, maybe that can be used for detecting metabolic disorders or other things that's related to these chemicals. Okay, I want to use this technique to illustrate again the example of training how to juggle. Okay, throwing 3 balls at a time, 4 balls at a time. Okay. Okay, imagine while you are learning things. Okay, you need to be flexible, right? In general, learning new things, you need to be flexible. If you are a stubborn person, you can't learn new things, right? You need to be flexible. Okay, because if you're stubborn, you don't want to change, then you can't learn. Okay. The implication is that inside our brain, we need stability, okay? Why we need stability? Today you are this person. Next day you are a similar person, right? You won't be too different. And this is because of the stability that you have in your brain, okay? Such that your previous behavior okay, that you always do. For example, I always brush my teeth in the morning. I am a basketball player, I'm a football player, then I can do this skill very well. I've learned that before, and I want to be stable that I can still perform that. Okay, so that means that you need some stability. Okay, when you're learning, you are actually disturbing your stability. Okay, mostly in a good way when we talk about learning. Okay, but you need to disturb your stability. The implication is that inside our brain, there are chemicals to keep us stable. There are chemicals to keep us excited. Okay. And normally we need to strike a balance between them. Okay. These two chemicals are exactly what I mentioned before, GABA and glutamate. GABA is the excitation guy. Sorry, glutamate is the excitation guy, and GABA is the inhibition guy, okay, to keep us stable and keep us excited for the other one. Okay, now the story is that while you're learning this new skill, how to juggle, as we said, well, some part of the brain for eye-hand coordination should be used a lot, right? And you also need to be ready to have some disturbance in this area, okay? You need to get prepared to learn new things, okay? Such that you can learn the skill. You change your behavior, okay? And in fact, this was the case when these researchers tried to look at the brain composition of a eye-hand coordination region in the brain, which is this region in red, okay? And when they tried to measure the chemical composition, they found the following. So what they did was to look at this GABA chemical that is for stability before they started the training. They have a certain level of GABA in that particular part of the brain, right? So the GABA is of some level. During training, the GABA level went down, okay? That means that they are more ready to learn new skill. They are more ready to change. So that's why there's less GABA for less stability, for more readiness to change. Okay. After they have finished the training, the GABA level went back up, okay, to keep the stability. Okay. So that gives us a good example of how we can measure brain compositions, chemical compositions, and then how this is related to our experience, our changes and learning. Okay, now I'm giving you this third example of a function of MRI scanner, which is to measure brain activity, okay? The thing that I feel most excited about, okay? Because, well, if you're taking picture of the brain, well, it's a static picture. It tells you nothing about brain functions, okay? When you are memorizing things, when you're learning things, what does the brain do, okay? We can't use structural scan to tell us, but we can use functional scan or fMRI to tell us that, okay? So this is a technique, again, using the same machine to measure brain activity across time, okay? So it gives us a moment by moment measure of the activity of the whole brain, okay? So let me, well, depending on the time, I would tell you different examples of using fMRI. For example, task-based and resting state fMRI. Okay. Again, well, fMRI, if you are juggling, okay, of course, you expect that you need to use the part of the brain for eye-hand coordination. Now, with fMRI, we can detect it, okay? But how? Of course, the limitation is that you can't ask your volunteer or patient to lie inside the MRI scanner and juggle inside, right? It's a very tiny space, and you probably can't ask them juggle there. Okay, that's one. The other is that you also want them to keep as still as possible. Okay, so juggling may be a bit hard. Okay, but maybe you can change the context slightly. Okay, to ask them to do some motor response. Okay, so for example, you can ask people to move their finger inside the MRI scanner or to move their wrist, okay, inside MRI scanner and see what happens inside the brain. See which part of the brain is being activated. And yes, it is possible to do that using fMRI, okay? So normally with fMRI, you give people a task to do inside the MRI scanner. Normally the task don't need the person to move around. They can lie still inside the scanner and then engage in a task, okay? Like moving a finger to check parts of the brain for motor responses, or you can ask people to memorize something inside the MRI scanner. You can even ask people to play a video game inside the MRI scanner and to see how that happens inside the brain. What does the brain do while people are playing a video game? Okay. Okay. Another example is to look at something that we call resting state fMRI. Okay. The fact is that our brain is working 24 hours, 7 days a week. Okay. You might have heard of myth saying that, well, we are just using 20% of the brain, 30% of the brain. Okay. The remaining 70% is not used at all. Okay. This is myth. Okay. The truth is that we are using the whole of our brain at all time. Okay. But different parts of the brain would be oscillating. Okay. They might be synchronizing. Okay. They might be communicating in specific ways. Okay. And then we can use this technique called resting state fMRI to do that. Okay. To find out these communications across brain regions. Okay. What we do normally is that we ask people to stay inside the MRI scanner still. Try not to fall asleep, although it is hard. Okay. Try not to think of anything else. Just lie there. Very difficult job. Okay. Because thinking of nothing is itself a very difficult task. Okay. But then by doing that, we can see that there might be some areas inside the brain that they might have synchronized activity. Okay. When one brain region gets activated at a time, the other region will also get activated. Okay. Showing us communications of different parts of the brain. Okay, now resting state fMRI. Okay, so what would be the use of resting state fMRI? Here I'm showing you again the example of juggling. Okay, so now we are talking about after learning this skill, then perhaps you should have better eye-hand coordination, right? And then supposedly the region inside the brain for motor movement, okay, so for moving your hand, for example, and the region of the brain for seeing things, they might be better communicating after the training. Yeah. And that was really the case in this example, that that was the hand region or the motor region, and this is the seeing region, okay? And then this tells you how much synchronized that they are, okay, for these regions. Before the training, they are synchronized in certain level, in certain ways, but after the training, they are even more synchronized. They are communicating even better afterwards, after the training. Okay, now I've talked about a lot of nice things about MRI and fMRI, okay? A piece of good tool sometimes are being used a lot, sometimes in very good ways, but sometimes also in very bad ways, okay? If you want to learn more about that, I highly recommend this paper, okay? What we can do and what we can't do with fMRI. Okay, I think I'll skip this. Is a little bit of history how this very clever Japanese person discovered fMRI more than 20 years ago. I think he's in Osaka now. This person called Seiji Ogawa. He's in Osaka, and I think almost retiring. Yeah, well, should have retired, but still quite active in research. All right, I'll skip these technical stuff because of time, and I think it is even better for me to spend a bit of time talking about these last few slides. Okay, why are we so excited about fMRI? Not just because that we can, well, use that to understand brain functions, but just very recently, I think with a little bit of development in AI and better mathematical models, we start to be able to use fMRI in some interesting ways. For example, this study, which was published more than 10 years ago already, have already got this idea of how we use fMRI in the following way. Dream decoding. Dream decoding. Okay, I'm not talking about fortune telling here. Okay, if you see a baby in the dream, then something might happen, or if you dream of losing your teeth, what will happen? Not that kind of thing. Here, I'm just talking about capturing brain activity while people are asleep. Okay, and then based on brain activity, to reconstruct or to guess what they saw in their dream. Okay. This was already feasible more than 10 years ago. Okay. So what this experiment was about is that they asked volunteers to stay inside the MRI scanner, sleep there, okay, overnight. It would be like that gentleman's concern just now. Very noisy environment, okay? But perhaps these Japanese people are tolerant enough, okay, or tired enough, so that they were able to fall asleep. Okay, I guess this kind of experiment is better done in Asia, where people are sleepy all the time. Anyway, it's safe. It's safe to stay inside MRI scanner for a very long time, and then these people's brain activity are being captured. Okay, some part of the brain would be indicative of what they saw inside the dream, okay? Because we have in our brain a huge area devoted for seeing things, okay? And it's possible, okay? So these people basically got the data of brain activity using fMRI, and then they decoded what they saw inside the dream, okay? And that was quite a good match, okay? If you are curious about the decoding, you can look at the paper. They even have a video of decoding the images that these people saw in during their dream, okay, and try to match with their actual dream that they reported, okay. So you can find that out from the paper. These were two dreams reported by the volunteers. I'll leave it to you to read. But now, after 10 years, this kind of technique got even more advanced, mainly because of better mathematical models used in AI and other things. Now, here I'm showing you this example where there's another group of researchers that they take pictures of the brain. Well, not take pictures, but they measure brain activity while they're given some pictures. Okay, so they're given these pictures. They're seeing them, and then something should have happened inside the brain. So there should be some activity inside the brain such that they can consciously see this picture and then they can remember that, okay? Now, what these people do is just to keep an eye closed. These researchers, they keep an eye close to the actual pictures, okay? They just look at the brain data and then use a computer to reconstruct what they saw inside the picture, okay? And then here I'm showing you the matches between the actual picture on the left. Okay, these are the actual pictures. And then these are the reconstructions, okay, of the picture. And then you can see, well, strikingly, it is quite similar, okay? So just based on brain information, then people or researchers can already guess what they saw from their eyes, okay? So this is something that can be achieved these days. Okay, now this is the last slide I would like to share with you before we go to a break. Okay. So these functional scans, well, they are interesting in some ways. They may also be clinically relevant. Okay. Here I'm showing you another example of a case. Okay, this person, Dante Page, an American. Okay, so he was caught, okay, because he brutally raped and murdered a person, and the defendant was brought across state to be scanned. Okay, now try to get the brain activity. Okay, because some reasons, because this person had a very unfortunate childhood. Okay, um, he got severe physical abuse and got head injury in his childhood, and that was documented. Okay, and then he was asked to uh, take these brain scans, and while being scanned, he was asked to perform a task that requires him to inhibit some impulses. Okay. Now, of course, well, as you may be able to guess, he is poorer in controlling his impulses. And inside the brain, that is reflected to reduce activation in some part of the brain, like these ventrolateral, ventromedial, and polar prefrontal cortex. Okay, the name again don't matter that much in this lecture today, but these regions again are related to impulse control, like the orbital frontal cortex that I just mentioned, which is just next to these regions. Okay, so maybe that could be related to the crime scene that he raped somebody and murdered somebody. Of course, can we use this as an excuse to spare him from any judgment or some consequences? Of course not. But then the court considered that as a piece of evidence. Okay, and he was spared the death penalty at the end and given imprisonment. Okay, so something that might be relevant in our real life situations, that these brain scans looking at brain activity could help us to reflect some reduced functioning of the brain. Okay. All right. So today I think I have covered three things. Well, overall, telling you a conventional use of MRI to look at brain structure. I also introduced the machine, mentioned how we can use that to measure brain chemicals, and then finally talk about how we use that to measure brain functions. Okay. All right. Any questions? Any questions?
I have a question. You are talking about the resting state of the MRI's usage, and I'm wondering, some coma patient, seriously, some goes to vegetation state. Can MRI distinguish the problem, or even can distinguish
Coma
it can
patient,
be
right?
certified for abortion of maintenance of state
Right, like those
life
with
and
vegetative states, right?
yeah.
Take my yan. Okay. Yep. All right. Very good question. That relates to research spearhead by somebody called Adrian Owen in Canada. Very nice work. That some patients that are in vegetative state They are not real vegetative state patients. They are suffering from a problem called lock-in syndrome. Okay. Okay. What is this about? Is that for vegetative state? I guess from popular culture, like TV shows or whatever, you have an idea, right? They can't move. Um, they may still have their eyes open and closed at different time. Okay. They might still show some basic reflexes, but you just can't communicate with them. They just can't respond. Okay. And that is a typical uh, uh, observation with patients with vegetative states. But some patients, they actually have a problem called lock-in syndrome, where they can actually still sense the world. They are still conscious. They just cannot voluntarily respond. Okay, that means that they can still understand the words. They just can't talk. They just can't move their body part purposefully. Okay, these are patients with lock-in syndrome. Okay, now going back to fMRI and this Canadian person called Adrian Owen, and what they did was that they tried to scan some of these patients that they thought would be in a vegetative state. They tried to communicate with them, okay, and notice that actually some of them are actually conscious. And then, for example, how they can do it is that they scan these patients inside MRI scanner. They talk to them, although they are not sure whether they can understand the researcher's words or not. They just talk to them. For example, imagine playing a tennis ball, throwing a tennis ball. Okay, that would be a kind of motor response. Okay. Supposedly, if a person can understand the words, they would be imagining playing tennis, and then the motor part of the brain should show some activity. Okay. And now the interesting thing is that this is really the case for some of these patients thought to have been in a vegetative state. Okay. So now that actually gives us some opportunities for these patients to be able to communicate using brain scan methods or other kind of neuroscience methodologies. Okay, I guess nowadays we talk about implanting chips, right? Um, for example, Elon Musk's company trying to implant chips in patients, and perhaps this is another application of having these brain chips in patients' head, okay, or patient's brain. Yeah. Okay, there is another question online. Is it a more normal procedure to use MRI in mental disease, or whether it's a supplementary tool, subject to doctor's judgment? Okay, good question. I don't think that at the moment MRI is used as a routine for mental disease or mental disorders. In clinical settings, MRI is used more often in physical injuries, okay, or neurological problems like stroke, like head injury, or there's a trauma, okay, there's this kind of thing. But for mental health, way less often, okay. Um, I think it's because somehow uh, with mental health problem, it is harder for you to see any obvious structural abnormalities inside the brain or activity abnormalities. Okay, and that's why it is not a routine. Yeah, but the next speaker may tell you a bit more on that, right? Yeah. Okay. Any? Yeah.
Based on the resolution, is it possible to identify the blood vessels? Yeah.
Yes. Yes. It is possible to look at blood vessels. There are some specific type of scans that are very good for visualizing blood vessels. Yeah. I didn't talk about that today because of time, but yeah, it is possible. Yeah. Not just that you can visualize the blood vessels, but you can also look at the running direction of the vessel. Whether there's fluid running in the vessel, you can also see use MRI to picture that. Yeah.
You mean use the MRI to monitor the brain in real time? Yeah.
Yeah. Sorry, that was well, my description might be a bit misleading. Not that we can monitor it in real time, but in general, whether there's fluid floating of flowing that we can measure that, but in a static picture. Yeah, not something that you can do in real time. Not something that, for example, you use ultrasound to look at the heart. You can monitor it in real time. Not that kind of monitoring. Yeah.
But compare with other method, is it the best one to monitor the stroke, the blood vessels stroke?
In terms of visualizing, taking a picture, see whether some blood vessels are abnormal or not, that kind of scan, then MRI is good for that. Yeah.
But is it possible to locate which part of the brain to get stroke?
Oh, yes. With stroke, then, well, blood vessel got damaged, right? And then you've got a swamp of blood clot somewhere in the brain, and then you can visualize that. Yeah. The website that I included just now, I think they might have some example of stroke patients' brain. You can have a look as well. Yeah. Any other questions? Okay. All right. Okay, drink coffee. People said it make the brain more active. But what MRI told us about that? Oh, okay, whether MRI has told anything about drinking coffee, I think there should be a lot of papers or research about that. I am not familiar with that. I'm sorry. Do you know? Yeah, I need a bit of help.
Active medication. So there are a lot of psychedelic medication, and when people take these medications, you see different activity patterns. So I would presume that coffee would exert similar effects in the brain. Maybe not to the same level, but then you'll see certain patterns, definitely.
Yeah, I'm not familiar with coffee. I'm sorry. Although I drink that sometimes or quite often, especially well today that I'm having this lecture till late. I need to keep myself conscious. Okay. What are the areas of interpreting the images of all MR techniques? Okay. Oh, interpreting the images. It's a very broad question. Of course, if we are talking about interpreting structural scans, that is subject to human errors, right? Because, well, we rely on people to interpret the pictures. Sometimes, let's say we are talking about tumors. With a large tumor, it's easy to identify, right? But in real life, you have a lot of marginal cases where the abnormalities are small, right? Not obvious, gray areas. Then it would be subject to people's judgment. Of course, we would expect that the medical doctors, the radiologists, the neurologists, they're experienced enough, they would be able to give you reliable judgment. Nowadays, of course, with AI, there are more and more of that examples using the computer to locate these abnormalities. Again, quite popular these days. Yeah. Okay. Oh, okay. Interesting. There's a question that there's a person working on trees and other vegetations and any application of MRI in plant science. So we're moving away from neuroscience to plant science. Okay, let me tell you this case. Every year I run a neuroscience course, and I need to run some demonstration with the MRI scanner. Just now, this gentleman asked me about ways to visualize blood vessels. Okay, there are other things that contain fluid inside our brain that can be visualized using MRI scan. Okay, in this course, I want to demonstrate that the MRI scanner can visualize these vessels or these fibers that has water or fluid flowing through it. The university doesn't allow me to use MRI scanner to scan a student for teaching reason, which is annoying. Okay. Then what I had to do is to buy some celery from the supermarket. 西芹啊, celery, because it's fibrous. Okay. And scan the celery inside the MRI scanner. So for this question, the answer is yes. You can use MRI for plant sciences, depending on what you want to do. I set an example where you can, well, use MRI scanner to look at the flow of the fibers inside celery. Okay, then the short answer is yes, feasible. There's another question. Some people are more aggressive than the other. Is it related to the prefrontal cortex? Simple answer is yes, maybe. A more conservative answer would be that somebody being impulsive could be due to many reasons, right? Yeah. So the prefrontal cortex could be one of the many possible reasons. Okay, I don't have any more questions from online. And any other questions? Great, nice. Really enjoyed. Very nice questions. Very good interactions. Okay, I think that's it for my part. Why don't we have a Why don't we have 10 break for 10 minutes?
All right. So, hello, everybody. Welcome back to the second portion of today's lecture. My name is Dr. Cheng-Ling Su. I'm an assistant professor from the Department of Rehabilitation Sciences. So I am a colleague of Professor Bolton Chow. And for my part of the talk today, I'm going to be talking about this idea of reserve and resilience. So this is going to be a continuation from Professor Bolton Chow's talk on MRI and applications of MRI. I will start with just the very surface level about what reserve and resilience is, and then I am going to dig a little bit deeper and talk about the application of MRI and how neuroimaging is used to study resilience against aging and other sort of diseases like mental health issue, for example. So, all right, so this is a quote from an ancient Roman philosopher, Cicero, and I find this quote really beautiful. It portrays this idea of resilience really well. So it says, "Old age is the crown of life, the final act in the play of life." So the reason why I really like this quote is because it dignifies this very, very well-defined defense against aging, that aging is not just a burden, it's not a disability. And there's certainly cases when people can age well, age really gracefully, and have healthy aging such that they can still be a very contributing members of the society. So this is the point where researchers like myself who studies resilience and reserve are trying to get to trying to make people able to get to that point, such that old age, or the last stage of our life become the crown. And it is not until the early 70s when we start to get more empirical evidence on resilience and reserve. So Norman Gartman-Z, who is an American psychologist So he started out looking at resiliency in children with different socioeconomic status and how they can be resilient against their background and develop into a contributing member of the society. And he later on looked into expanding on looking at schizophrenia and resilience in schizophrenia. And then we fast forward a few decades until 2024. So this is when the Lancet Commissions reported that life course development of resilience towards mitigating development of dementia becomes one of the most important research priorities for researchers, because that's the only way we can start looking into preventative methods against development of dementia. And given the fact that our society is aging at a very, very rapid rate, this is going to be especially important. And here in Hong Kong, we are one of the places in the world with the longest living human being. So this is going to be essential for us to figure out ways to help people become more able when they get older. So I just spent a few minutes until now talking about what makes resilience research important, but what is it exactly? So the operational definition of resilience is this empirical observation of a phenomenon when an individual do not develop symptoms, disorders, or dysfunction when they are subjected to adversity. And here, when I say adversity, it can be a whole range of different things. It can be based on conditions, it can be acute condition, or it can be chronic. It can come from different sources like social interaction, mental illnesses, or physical stressors. But the key point here is that resilience is an outcome-oriented measurement. It is not a static property. It is often measured across time. So we're looking at the dynamic process of how it changes across time. And if we look at this figure here on the screen, so let's focus on the top one first. So this top figure is a model of resilience. And on the x-axis, we have time. On the y-axis, we have the well-being of an individual. So this is a trajectory of a person's wellness across time. And if this person is exposed to trauma or traumatic events, and these events, again, can be acute or it can be chronic, but through the accumulation of these traumatic events, there's going to be a time point when the onset of decline starts. And this is when, in this case, mental health deterioration occurs. And then this decline will happen all the way until a point where it plateaus and they start to experience more of a recovery process. And then if we set a threshold somewhere along this line or this process, the person after recovery will get back to its normal state. So that would be a very typical classic model of resilience. But now if we look at the bottom figure here, so assume each of these lines reflect the trajectory of one single individual. This very bottom gray solid line here would reflect someone with very low level of resilience against trauma. Why do I say that? Why do I say that? Because you see, when the person is exposed to trauma, and then you see this onset point again is when the person starts to deteriorate, but then for this particular person, they never recovered, right? So this is a classic representation of someone who has low level of resilience against this trauma. Now, if we look at the top dotted gray line here, now this curve is very different shape compared to the other ones. For this particular individual, you see they are exposed to the same trauma, and the onset is the same. So the accumulation of traumatic events or markers of this trauma is the same. The onset time is the same, but then the deterioration is not the same. So you see they deteriorate, but they don't deteriorate to the point similar to this person. So it's very different level of deterioration. And then recovery process occur much faster compared to even the model that we mentioned here. So in this case, this person would be classified as someone with high level of resilience. So you can imagine now, when we're talking about resilience, we're less focused on the pathophysiology. We're not super interested in the mechanism of how a person develops a disease. Instead, what we're interested in is what mechanism unfolds in the person that help them maintain their health. So it's more health focused rather than disease driven. And the expression of resilience can come from different forms. So it can be partial or complete absence of signs of illness, or it can be an active adaptation mechanism that's expressed either through neuroimaging or other sort of measurement devices. And classic examples of how this has been implemented in research is in studies that look at, for example, PTSD, post-traumatic syndrome disorder, or depression, addiction, and so on. But the underlying assumed pathophysiological process is shown in this figure here, whereby it is the spectrum. And on one end of the spectrum, we have people who are completely healthy, free of any marker of that pathology. On the other end, we have people with most likely an accumulated amount of that marker or pathology such that they start to exhibit symptoms. And resilience is this vertical line that sort of serves as almost like a barrier that protects people against moving towards or progressing towards having overt symptoms of that pathology. So surely these people can still have these markers of that disease or pathology, but they can accumulate to the point of that barrier, but they never cross that barrier towards becoming symptomatic. So that's where resilience does its magic and protect people against decline. And another appeal of why we're interested in looking at resilience and reserve is because many of us here probably are well aware that a lot of the clinical disorders are not independent. So these are oftentimes comorbid diseases, meaning that there are a lot of overlapping symptoms and overlapping dysfunctions. So if that's the case, then someone with resilience against a certain dysfunction could very likely be resilient against other type of disorders. So on the right-hand side of this slide here, I have a illustration demonstrating this stress response system. This is very famous. It's the HPA axis. Though a lot of times when people undergo stress or stressful situations, your body goes through this circuit, and then cortisol gets released into your system. And we do know that cortisol dysregulation is associated with a lot of these mental health issues like depression, bipolar disorder, borderline personality disorder, and schizophrenia. So again, coming back to my example here, if someone is resilient against a specific type of dysfunction here by having a way to mitigate this stress response system such that there's no dysregulation of cortisol, then likely this person is not only resilient against, say, depression, this person can also be resilient against bipolar disorder, for example. So I've talked about what resilience is and how they're expressed in some clinical situations. Now I'm going to focus on explaining what are some of the components of resilience. So we have resilience factor, and then we also have resilience mechanism. So the factors are not to be confused with the mechanism itself. So these factors are any variable that is able to be quantified, and we can use it to predict positive outcome. An example of that would be, for example, your personality trait, social support, lifestyle, behavior, or executive function. So it can be internal or external factors. So in this table here, I know the words probably a little bit small, but what I want you to do is just shift your attention to just the blue column and the yellow column. So the blue column are broken down into different domains of potential decline that a person can experience. And the yellow column are the corresponding resilience factor for that domain. So for example, for cognitive and behavioral decline, the resilience factors would be something like strong executive functions, good coping efficacy, or cognitive flexibility, for example. And then for the other ones, we have things like good regulation, good social skill, good sleep habits, being physically fit, have good nutrition, and so on and so forth. On the other hand, we have the resilience mechanisms. So these are processes in your body or in your brain that leads to someone becoming resilient against a certain condition. And in the literature, a lot of times people discuss this as either a coping, compensatory mechanism, or efficiency mechanism. And for example, the ability to flexibly adjust to adversive events that can trigger a stress response, such as the HPA example here, would be considered a compensatory or coping mechanism. For example, if someone can cope against stress really well, such that they don't trigger this response system, then again, you don't get this potential cortisol dysregulation happening in your body. And that could prevent development of mental health disorders. All right, so here are a couple of examples of resilience mechanism has been done by behavioral experimental studies. So this particular study, they're interested in looking at the relationship between childhood trauma and depressive symptoms. In this study, they included 6,400 individuals between the age of 9 to 17-year-old, and they defined resilience factor using this scale called the Connor-Davidson Resilience Scale. So this is a 25-item questionnaire that is used to assess stress coping ability. And then for this study, they quantified depressive symptoms using the Center for Epidemiological Study Depression Scale, the CESD. Again, it's a 20-item questionnaire that's widely used to assess depressive symptoms. So on the left-hand side, I have two figures here. Again, they're relatively small, but I'll verbally explain and describe what these models are. So these are two classic models that resilience researchers use quite a bit. So I do want you to orient you to these two different models. So the top model is what we oftentimes describe as a mediation model. And the bottom model is a moderation model. So these are statistical models used specifically to look at how different variables are interacting with each other. So for the top model, I'll break it down to simplify things a little bit. Now, ignore the top part of this model. So ignore the resilience factor here. Say if we're just looking at childhood trauma and depressive symptoms, and what they define childhood trauma is things like emotional abuse. Sorry. Oh, great. Thank you so much. Great. All right. So emotional abuse, physical abuse, sexual abuse, neglect, and so on. And for depressive symptoms, we have things like depressive mood, positive affect, somatic symptoms, and so on. So what this model shows, again, ignore this top part. What this model shows is that childhood trauma is positively correlated with depressive symptoms. And what that means is the more childhood trauma you have, the more depressive symptoms you will develop. So that's a very simple correlation, right? But now if we introduce this mediating variable into this model, it changes the story a little bit. Now, instead of going down this main path, there's also this secondary path that we can see here. And if you pay attention to the numbers on these secondary paths, you'll see there's a negative correlation between childhood trauma and resilience. Then there's also a negative correlation between resilience and depressive symptoms. So what that's telling us is that if someone is really, really resilient, have high level of resilience, the effect of childhood trauma will be diminished. And similarly, someone with high level of resilience will be less likely to develop depressive symptoms. So that's what this model is showing us, is that if you have a very strong level of resilience, then you're likely to be less affected by childhood trauma so that you don't develop as many depressive symptoms. So in this case, resilience is demonstrated as a protective factor. Now, moving on to the moderation model here. So moderation is a slightly different take on looking at how different variables are associated with each other. Moderations are more focused on interactions. So we're looking at how the moderator term, so in this case, the resilience, is interacting with the independent variable, which is the childhood trauma. So we're trying to see what is the interaction between resilience and trauma. And what this data is showing us from this study is that if you, again, look at the correlation number here, and at the very top, we have low resilience. The second row here is the medium resilience, and the last row here is the high resilience group. And you can see that the number changed significantly between the low versus the medium. So that means as long as someone has medium level of resilience, you'll start to see a significant protective effect against trauma. All right, so this is another example of how resilience is in play. So this one, they're looking at survivors of traumatic injury that requires surgery, and they assess perceived coping efficacy at different time points across the study, at 1 month, 3 months, 6 months after surgery. And then they defined 4 different groups of patients based on their outcome. So they have a group that has chronic distress, they have a group that has delayed distress, a third group with gradual recovery, and the last group that shows higher level of resilience. So the chronic distress is illustrated by this top line here. So these are people who are chronically across time that shows high level of stress, either is post-traumatic stress or depression. And then the delayed distress is this group shown by this triangle line here, that they started out with a moderate level of stress, but then at a later point in time, you see this significant spike in terms of their stress level. The gradual recovery is shown by this square line here, that you see a gradual decline or reduction in the level of stress. And then the resilient group is this very bottom line here, that you can see that the stress level is at a very stable level across time. So obviously this is the best group, right? But what's really interesting from this study is that the finding suggests the effectiveness of coping mechanism seems to have a very variable effect. So here, what we found, the study found, is that the chronic distress group are people who had the lowest level of perceived coping efficacy. So these are people who seemingly don't have a lot of confidence in their ability to recover from the injury. And that's why they're always at this very high level of stress. And the really interesting part here is this second line here. So these are the people with the delayed distress. And these are actually people with the highest level of perceived coping mechanism or coping efficacy. And now that's kind of surprising, right? So these people have the highest efficacy, but why do they show this trend of spiking at near the end of the study? So this comes back to what I mentioned earlier from that table, is this notion of realistic optimism. So these people likely do not express or exhibit a very realistic level of optimism in terms of their recovery process. So when the expectation and the outcome don't align, you can see this increase in stress level. Now the last group, or the best group, is the people with the intermediate level of perceived coping efficacy. So somewhere in between these two group is the best. So again, coming back to this idea of what's practical, what's realistic becomes very important here. Okay, so I just mentioned a couple of studies on behavioral experimental design that show us the effects of resilience in stress and depression. Now, what I want to show you is to shift gears and talk a little bit about imaging. Before I do that, I want to show you this picture. And I would like to ask the audience here, can anyone here take a guess on what this thing is about? Like what are we doing with this thing? Can anyone guess what this thing is? I can give you a hint that this is not an 18th century torture device. So this person is not being tortured. He's being measured, but he's not being tortured. Can anyone guess what this could be? I see something say measuring heart rate. Very close, very, very close, but not exactly. Anyone else? So pay attention to, um, pay attention to this part here. So there's a platform on which a person lies on top of, right? And right underneath this platform near the middle, there's another block of, I don't know if it's wood or other material, but that serves almost as a fulcrum. So that turns this platform into a scale of some sort, like a seesaw. Now, what happens is the experimenter would ask his participant to think about or to perform a very cognitively demanding task. For example, calculating some very difficult math question. And what happens next is super interesting, is that this part of the participant or the seesaw goes down when the person is engaged in cognitive task, and the feet portion goes up. So it becomes tipped. So the balance is no longer balanced. But when the person goes back to the resting condition, the scale becomes balanced again. Now, does that remind you of something that Professor Bolton Chow just mentioned in his talk? So this is measuring, basically what this shows you is that when someone's engaged in cognitive task, there's increased blood volume to the brain so that it gets heavier, so the balance becomes tipped, right? So that's almost like the MRI, isn't it? Because MRI, obviously, we're not measuring blood oxygen level dependent signal here, but I would probably venture and guess that this likely is the first ever human-made neuroimaging device based on the time. I don't know if anyone else knows anything that's earlier than this, but based on what I know, this is probably the first evidence of human-made neuroimaging device. So I thought that was really cool to show you guys. But extending from that, as you learn from Professor Bolton Chow's talk, there are different methods we can use the MRI to measure different properties of the brain, including things like structural morphometry, structural connectivity using diffusion weighted imaging, or we can use fMRI to measure brain activity, to measure brain activity or connections between different parts of the brain. And that can inform us of your brain network architecture, both in terms of structural or functional at a functional level. But I'm not going to go into too much detail here because we already learned a lot from Professor Bolton Chow. But instead, what I'm going to show you are some examples of evidence that how imaging has been applied to study different mental health conditions. This particular case, we're talking about, again, stress and cortisol level. So this particular study was looking at how brain respond to different stress levels. And we have two groups. We have a control group and we have a stress group. So stress group are people who underwent stimulus that makes them a little bit more stressed. And they measure their salival, cortisol level in their saliva. And you can see that in this stress group, they show this increase in cortisol level as they are engaged in tasks that makes them stressful. And then this level of cortisol maintained for a period of time until the task is completed, and then it tapers down to a level that's close to the control group. And on this graph, this is subjective level of stress. We see a very similar trend when the stress group shows an increase in the perceived level of stress, and that kind of maintained until near the end of the task, and then it goes back to the level that's close to the control group. Now, what they did is also they look at the brain activity pattern of these individuals, and they found that the difference between this increase in cortisol level compared to the control group was reflective of specific regional activity in the brain. So you can see from graph A, so the control group activation is shown by the red areas in the brain. So these are the area that's activated when it's under the control condition. And the, I guess this is like a blue purplish color. So that's the area when the stress stimuli is being presented. And compared to the stress, compared between the stress and control condition, the two areas that were particularly showed higher activation level is the prefrontal cortex and the precuneus. So these are the two areas in the brain that show significantly greater activity when a person is under stress. So these are two areas that seems to be really sensitive to stress response. So this is another example. So this was a study done by Luo in 2024. And again, this is looking at brain activity level and using a different way to calculate brain activity level, but this time they're looking at activity during rest. And they use, again, what I mentioned earlier, a moderation analysis to look at whether activity in a very specific part of your brain can protect people against trauma. Will protect people against development of depression due to trauma. I think I should clarify that. And what they found is that the activity level of the middle temporal gyrus seems to be a protective factor, or that part of the brain seems to have a protective role in protecting people against depression. So it's specifically people with low level activity, as shown by the graphs here on the bottom. You can take a look by expanding. Right now, I think I can't really highlight the specific parts, but later on, feel free to expand that figure a little bit. But what these four figures are showing you is that people with low activity in this middle temporal gyrus region have the best chance against developing depression due to trauma. So this area of the brain seems to be a good marker for targeting. So say, for example, if you want to conduct a treatment, this area could be a good marker for that targeted treatment. So other than activity, as Professor Bolton Chow mentioned, we can also look at connections, right? So connectivity between areas of the brain. So here, this study, they're looking at connectivity of this area called supramarginal gyrus. So this area shown here. So they're trying to look at the connectivity of this region and how that can mediate the benefits that people get from social support in lowering depression severity. And they found that the pattern of connections in this area of the brain, the supramarginal gyrus, does in fact mediate this relationship. And this mediated relationship is also moderated by interpersonal security, as shown by this moderator term here. So how this area is connected to other parts of the brain will dictate how much benefit you get from social support in lowering your depressive symptoms. Okay, so there are other mechanisms of resilience that I think I should mention, including brain maintenance. So brain maintenance is defined as this absence of change in the brain. So this absence of change demonstrates resistance to insults or damage to the brain, regardless of where the source of that damage comes from. It can be due to aging, it can be due to pathology, but the emphasis here centers on change over time. So we want to see as little change as possible to indicate a good level of brain maintenance. So this reflects a passive model of resilience because your brain is not actively trying to change itself to promote resilience. So instead, your brain is just able to withstand insults. And on the left-hand side here, I have two images from two people who are relatively around the same age. But you can see that the left brain is obviously less, have less integrity compared to the right brain due to all these gaps and spaces in the brain, right? So even though these two people are around the same age, but this person is able to maintain their brain integrity at a much higher level compared to this person because there's very little age-related change here that you can observe. So, so in that case, you would say this person has a high level of brain maintenance. On the other end, we also have cognitive reserve. So cognitive reserve is another mechanism of resilience. It is a property of your brain that allows for clinical manifestation that's better than expected given how much exposure you have to adversity. So if you look at that definition closely, it's very similar to the definition I gave earlier for resilience. So this is talking about how well your brain can adjust itself so that you can maintain a certain level of function, even though you're exposed to some sort of disease or pathology. So this reflects instead not a passive but an active model of resilience. Because now in this case, your brain is actively changing itself to adjust for the adverse event that they experience. And here on the bottom, I have a figure to demonstrate that, that framework. Here is on the x-axis, we have AD pathology. Here is moderate level of accumulation of AD markers, for example, tau or amyloid plaque. And here is the mild amount of accumulation of AD pathology. On the y-axis, we have clinical severity, and you can simply think about that as cognitive performance, for example. So we have people who are normal here near the bottom, people with MCI, mild cognitive impairment, people with mild AD, and people with severe AD at the top. So if we look at this stage when people have moderate level of AD pathology, the two lines here, one representing low reserve, one representing high reserve, you'll see that both of these lines are classified under the mild AD group, right? So both of these, so under this line here, they're all part of this mild AD classification. But if we look at the mild case, the people who are along this low reserve line still classify as mild AD. But for people with high reserve, you see that they're in fact not classified as mild AD, but rather people between normal and mild cognitively impaired status. So you see that there is a protective effect here for cognitive reserve and how they protect against AD pathology. So here's an example on cognitive reserve and how that can potentially protect people against lesions, white matter lesions in the brain from developing depression. We know white matter damage is a major contributor to late life depression. And this study, what they found is through using a moderation analysis, again, looking at these two lines here, they showed that those with higher level of cognitive reserve were less prone to developing depressive symptoms due to white matter damage. And here's a study that was conducted by my PhD student. What she did here, she used education attainment as a cognitive reserve proxy. So proxies are not indirect measurements of that variable. So cognitive reserve proxy, oftentimes, if you look at the literature, they look at education attainment or years of education obtained, and things like IQ or occupational complexity. So these are all proxy measurements of cognitive reserve. And what she was interested in was to look at the effect of education attainment and see whether that can protect these group of population with physical frailty. So these are older adults with physical frailty. And she wants to see whether education can protect them against the effect of aging on cognitive decline. So what she found is, yes, education does help, and the magic number for this specific population seems to be 8 years. So if you have 8 years of education, and if you happen to be also physically frail, you will be less prone to cognitive decline compared to people with less than 8 years of education. And this is another study conducted by another PhD student I'm co-supervising. So for this one, she was interested in looking at how the brain networks using MRI, derived using MRI, is underpinning this relationship between white matter lesion and executive function decline. And again, using moderation analysis, she found there are 3 different networks illustrated by these 3 different graphs that seems to be involved in this protective mechanism. So the first one is the default mode network. And for this one, she found that the lower, actually the lower the connectivity, the worse the protective effect. So this particular network, you want it to be more connected to the regions within itself in order to receive the most benefit. And the second network is a frontal executive network. And for this one, you want lower connectivity instead of higher. So you want you don't want this network to be connected to itself. You want it to be connected to other networks in order to get the effect. And for the last network, the relationship is very similar. You want it to connect to other networks instead of itself. So now I've spoken about cognitive reserve. I want to spend a few moments talking about this new construct of reserve called physical reserve. So this is an area of research I'm actively undertaking at the moment. So similar to cognitive reserve, physical reserve is defined as the individual's ability to maintain their physical function in the face of age or disease-related changes in the brain. So you recognize that definition is very similar to cognitive reserve. You just flip the cognitive function or replace it with physical function, and you get the same, you get this definition. This was first proposed by Professor Roy Hoser, my colleague from the Albert Einstein College of Medicine. And he used this method called residual variance modeling. I'm not going to get into the detail of how that modeling goes. That's kind of beyond the scope of today's talk. But he used this method to empirically prove that this is a more direct measurement of reserve. So this is no longer a proxy measurement of reserve, but this is a more direct measurement of reserve. And what he found through his study is that physical reserve is related to cognitive reserve, but they're distinct from each other. And that reflects this bidirectional relationship that we often observe between cognitive function and mobility function. But in this study of 500 older adults, what he found is that physical reserve was correlated with lower incidence of falls, so it protects people against falls. And the but he concluded that in this study, the mechanism underlying physical reserve may be involving a lot of different sort of allocation of neural resources in the brain, and how they can utilize those resources to undergo compensatory process that's facilitated by large-scale networks in the brain. So this is their hypothesis, but they cannot demonstrate that through their study because this particular study do not have a neuroimaging component. So as an extension from this study, so this is just a table illustrating that physical reserve they calculated was correlated with walking speed and cognitive function. So as an extension from their study, I worked in collaboration with Professor Roy Hoser to conduct a study that used MRI as a way to investigate the underlying neural network associated with physical reserve. But before I show you those results, I want to show you this example. Now, this is an MRI image taken from my study and two individuals from my study. And if I were to ask you, now that you have listened to Professor Bolton Chow's talk, you guys are experts, MRI analysts, right? So if I were asked to ask you, these two brains, which one looks better and which one looks worse, what would you guys say? Top one looks better than this one, right? So you would assume the function of the top person to be better than the bottom person, right? But in fact, this is what we see. So these are two measurements for physical function. So the SPBB is short physical performance battery. The TUG is time up and go test. So both of these tests are for lower body assessment of your mobility. And you see the performance of these two individuals are actually quite similar. And if you really want to dig deeper, it's actually the person on the bottom that performs slightly better on the SPBB. So it sort of demonstrates that physical reserve does exist, because you can see even though the bottom person has quite a bit more atrophy in the brain, the person is able to maintain their physical function. So that really got us started to look into the brain a little bit more and explore what's underpinning this physical reserve capacity in the brain. So in this study, we tried to map networks associated with physical reserve in people with vascular cognitive impairment. And we really tried to dig down and dig deep and look at the relationship between reserve, white matter lesions, and postural stability. So this was a cross-sectional study with 38 older adults with vascular cognitive impairment. And here are their characteristics. I don't think we need to go into that in too much detail. And I'm just going to skip this slide because it's about the quantification of the modeling, which I think, again, is beyond the scope. And this is a processing pipeline for the MRI that we use to find the associated brain network related to physical reserve. So this is, after we quantify physical reserve, this is the data that we get. We stratify them into people with low reserve versus high reserve. And based on the characteristics, there are no significant differences between these two groups. And if we look at the amount of white matter lesion in the brain, we see that people with high reserve show slightly higher amount of white matter lesion, but this is not statistically significant difference. So you can say, arguably, these are very similar populations, even though one has high reserve and the other one has low reserve. Now, if we look at whether the reserve variable that we derived can protect people against white matter lesion, again, using this moderation analysis, we found that people with high reserve does indeed perform or is able to maintain their balance a lot better at higher white matter lesion load. And we also found there are specific parts of the brain that seems to differentiate people with low versus high reserve. And the pattern of connection is also very highly variable between these two populations. So for people with low reserve, they seem to engage more so in within network connection. So all the regions within that network are very tightly connected to each other. And relative to people with low reserve, for people with high reserve, instead of regions connected tightly to each other, the regions are more connected to other parts of the brain, other networks in the brain. And this is a similar case for this other network, that for people with low reserve, they're more engaged in within network connections. For people with high reserve, they're more engaged in between network connections. So what that is telling, before I go into what that tells us, is, again, demonstrating the reserve variable does protect people against lesion, and the network that we derive from the analysis also protect people against lesion. So we do know this is the network underpinning physical reserve. So what the result tells us is that these participants with lower reserve, they seem to exhibit greater connectivity within the networks, and people with greater reserve seem to exhibit greater connectivity between networks. So this shows us a very different patterns of engagement in within network versus between network coupling. So these differences may be reflective of how the brain with we think these people with high physical reserve is undergoing this very successful adaptive intrinsic mechanism because they're able to recruit, because they're connecting to other networks, so they are more able to recruit neural resources from these other parts of the brain. And similarly, for this other network, we found the same trend or same coupling patterns. And this, again, could be more representative of adaptive and efficient network organization. Yeah, so in summary, what we found in this study is that greater reserve can protect people against white matter lesions and help them maintain their postural stability through a more efficient network connection and better compensatory process. So up to this point, I've talked about behavioral examples of resilience, looking at how they impact depression or stress. And then I talk about different studies that look at the brain imaging results on these different populations and how resilience may be illustrated in those examples. Then I branch off to talk about cognitive reserve, physical reserve, and how these are also different components of resilience that's important to help people maintain cognitive function and physical function. Now, the next logical step and the last part of today's talk will be on how we can potentially increase reserve capacity. How can we build resilience in people? So there are a wide range of different strategies that people have proposed to study ways to enhance reserve capacity. These include things like cognitive training, mindfulness training, and also physical activity. And specifically, physical activity is the one that is most widely accessible to people and likely the most cost efficient, because doing exercise you don't need to spend a lot of money to do physical exercise, right? And you can do it anywhere, anytime. So before I talk about exactly what we found in terms of reserve enhancement, I think it's worthwhile to mention that exercise does have benefits on improving your cognitive function. So this was a study performed by my colleague Casio from the Concordia University. And in this study, he was looking at the effect of cognitive training in addition to aerobic training. And then he did this in healthy older women, and then he did both the cognitive training and aerobic training for 3 times per week for 8 weeks. And he found that the combination of these two improved executive function performance across the population. And in this other study performed by my other colleague, Kirk Erickson, he would look at the effect of aerobic training in healthy older adults. And what he found is that aerobic training does seem to improve your hippocampal volume. So it increases the volume of this particular part of your brain called hippocampus that's related to your memory function. So this increase in hippocampal volume after exercise was also correlated with better memory performance. So it not only increased the size of your hippocampus, but it also led to better performance on memory. Now, other than aerobic training, we have resistance training, right? Like weightlifting. So in this study done by my PhD supervisor, what she was interested in looking at is whether 1 time per week or 2 times per week of resistance training can improve function in these older women. And she found that twice per week of resistance training improved their executive function performance. And also that's reflected by changes that we observe in the brain, including, again, the middle temporal gyrus. That seems to be a common area in the brain that's related to these resilience factors. Now, this other study performed by John Best, again, look at resistance training. And what he found is that the impact of treatment conditions on changes in function and memory and white matter lesions seems to occur best for people with twice per week of resistance training. And specifically, it seems like people who do twice per week of resistance training is able to mitigate the effect of white matter lesion. So they're a bit more able to maintain their white matter lesion integrity. So this other study, this was done during my PhD. This is aerobic training in older adults with vascular cognitive impairment. And we found that aerobic training improved their executive function performance. At the same time, it reduced the activation level of areas related to this particular executive function. So what that's saying is aerobic exercise improves the performance, but at the same time, you don't need to activate your brain to a level to able to achieve that performance. So in essence, what this is saying is aerobic training is able to induce a more efficient brain function, because now imagine you can do better on a certain task, but you don't need so much activity in your brain to do so. So what about the effect of these different exercises on resilience? Can we see effects from aerobic training? Can we see effects from resistance training? And what about combining both type of training? Would that give us even better effects? So that's the question that we try to explore in this study. So in this final study that I'm going to talk about today, this is a randomized control trial. And then participants were randomized to 4 different groups. The control group, which is the balance and toning group, aerobic training group, resistance training group, and a combined aerobic plus resistance training group. And they did exercises for 60 minutes per day, 4 days per week for 6 months. And then we perform MRI scan before and after the training. So similar to before, we quantified this reserve variable. So we quantified content reserve and physical reserve simultaneously in this study. And then we stratified them into high versus low reserve and then examine their differences. So here, again, the various modeling, I'm not going to go into detail, but this is a result that we got from the study, is that combined training has the most effect in improving your executive function. And it seems like there are exercise-specific changes when it comes to expansions or increases in reserve capacity. With people that started out with low baseline level of cognitive reserve, compared to the control group, aerobic training and resistance training both improved their cognitive reserve capacity. So if you are someone with low cognitive reserve, you were to ask me, I would recommend you to go do some aerobic training to improve your reserve capacity. But if you're someone with high baseline cognitive reserve, again, aerobic training seems to be the best, but resistance training in this case doesn't really do much for you other than maintaining your level of cognitive reserve capacity. So moving on to talking about physical reserve, same idea. People with different levels starting baseline physical reserve capacity have a very different response to different exercises. For people with low physical reserve, compared to the control group, aerobic training and the combined group show the most increase in physical reserve capacity. So again, if you have low physical reserve and you come to me, you ask what sort of exercise should I do, I would probably recommend you to do a combined aerobic plus resistance training, because that increases your reserve capacity the most. But if you look at people with high physical reserve, the story is very, very different. As you can see here, none of the exercises seem to improve their reserve capacity. If anything, we can say aerobic training has a maintenance effect. But other than that, we can't say much about other exercises. And why is that? Well, currently, we don't really have an answer for that. We're postulating that this could be due to the study design. So if we go back to the study design, you'll see that this is a 4 days per week of exercise for 6 months. And specifically, if you look at the combined group, they're doing 2 exercises of aerobic training and 2 exercises of resistance training per week. And to a lot of scenarios, this most likely for people with high level of physical reserve, they're very physically capable. It's very likely that this is not sufficient for them to really reap the benefit from the exercises, because they're already starting off at a very high level. So chances are we need to design studies or design interventions specifically tailored for people with high physical reserve in order for them to get benefit from exercise. So moving on to looking at the brain. So between 6 months to baseline, we can see a lot of changes that happened. So this is a control group. We see overall, across every region in the brain, you see a very significant change over time. Aerobic training, you see this increase overall connections across different parts of the brain, not just within network, but also between network over time. Resistance training, on the other hand, we see more of a reduction in connectivity across different parts of the brain, illustrated by a lot of the blue connections. So all blue connections here, I should orient you before I talk about this, I apologize, but all the blue connection here indicates a reduction in connectivity. And then for the combined aerobic plus resistance training group, it does reflect more of the aerobic training pattern. So more between network connections. So again, just to illustrate this again, so here I simplified the graphs of the figure to only the most significant connection within the brain. And what we found is that indeed aerobic training does seem to increase between network connectivity more, and resistance training seemed to reduce between network connectivity and induce more of a within network connection. And then the combined group show, again, similar patterns of connection with as the aerobic training group. And this is a very interesting point that we also figure out here is that there seems to be one particular area in the brain that's really involved in both cognitive reserve and physical reserve. And this area is called the angular gyrus. And it seems like the exercise dependent changes that we observe may be underpinned by this particular area of the brain because it's consistently present over all the different groups. And to illustrate that this area of the brain does indeed help protect people against the effect of lesion, we did this moderation analysis, and we did see that this area, the connectivity of this particular area of the brain, does mitigate the effect of white matter lesion. Okay, so just to wrap up the talk, the take-home message for my part of the talk is that I want you guys to know that the active model of resilience is reflective of a property of the brain that tells it to functionally adapt to damages in the brain that you can potentially accumulate across life. And whether resilience is offered by one single network or multiple networks remains to be studied. So that's one area that we're, again, actively engaged in studying. Reserve is a measure of resilience that is modifiable, as illustrated by a lot of studies that we performed. You can see exercise seems to increase reserve capacity. And that takes us to the last point, is the most effective way to enhance reserve capacity remains to be established. But again, exercise seems to be one of the methods that are most effective. It could be the most effective one, but again, we need to do more experiments to confirm that. Okay, so I think that is the end of my part of the talk. And if there's any question, I would love to take them. Sure.
I can't help but think about that 70-year-old women doing weightlifting for an hour for a long time, for over 6 months or a long time, assuming they are not as active as the other group where you said they are very active. So after those women doing those exercises for a long time, would it be possible that they sleep better?
Yes, so
And sleep help them build their resilience. So my question is to you, is that, is your research or any of the research that you've come across consider the factor of sleep or dreaming that help people's brain develop healthier based on physical exercises, I don't know, walking, running, aerobic, or other form of exercises?
Yeah, that's an excellent question, and there are evidence that suggests better sleep in terms of quality. So if you look into the sleep literature, there are different parameters of sleep. There's sleep efficiency, sleep fragmentation, sleep duration, and there's WASO, which is like how long it takes you to get to sleep. So there are different parameters that we can measure when it comes to sleep. And there are evidence that suggests people with better sleep efficiency and less sleep fragmentation, they tend to do a lot better when it comes to cognitive performance and physical performance. So, but in terms of how sleep is affecting brain function, I think there are fewer studies that look at that, but then there are more emerging evidence on that as well. And I personally have done one study that looked at the effect of sleep on the brain, and we did see that people who have poor sleep, they have very disrupted brain connections compared to people who have good sleep. So I think your assumption that people with good sleep could potentially build reserve better is a very valid one. Although for the study that I just showed you, we didn't collect any sleep data, but I think that's one area that a lot of researchers, including myself, will be looking to build upon to see whether that in fact does play a role in enhancing reserve capacity. Okay, so let me take a look at the online questions. So what factor determine resilience? So the first question is what factor determines resilience? And as I mentioned during the talk, there are different factors associated with resilience, but it depends on what area, what type of resilience you're talking about. So if you're talking about mental health, that would be resilience factor associated with mental health would be very different from resilience factors as related to, say, physical or cognitive function. So it really depends which resilience domain, as I said, you're considering, and then the different factors would be very different. So that's a very broad question. So I hope that my answer is okay here. One other question here is I would like to ask why aerobic training and resistance training can improve cognitive function. Okay, yeah, so that's a very good question. So the underlying mechanism behind exercise and how that improves cognitive function is relatively well developed or well established. So there are different factors in your brain, for example, something called brain-derived neurotrophic factor, BDNF. And then there's also other chemicals in your brain, for example, IGF-1. So these are chemicals that seem to get produced when you're engaged in physical exercise. And these chemicals lead to proliferation of brain neurons, and then it gets you help you become your brain become more neuroplastic, and hence people presume that this is the pathway that the brain undergoes when you go through exercise and how that leads to better cognitive function. Improve neural network, improve neuroplasticity. So neuroplasticity and neural network, I don't know if this is the question that the person is getting to, but neuroplasticity and neural networks are two different concepts. Plasticity simply means how well your brain can adapt itself. And then networks are actual connections between different regions of the brain. So if we take this back to my example of exercise, exercise improves both the plasticity and also the integrity of your network. How can I know if I have high or low cognitive and physical reserve? Is there a simple way to measure this? Yeah, this is a great question. And it is something that we're trying to work towards as well. Obviously, I'm not going to be able to ask everyone to undergo the MRI scan and then for me to figure out whether you have high or low reserve. But we're trying to use the MRI data that we've collected so far, and then maybe with the implementation of machine learning and AI, we can use other ways to predict reserve capacity. But this is, again, still an area under a lot of research. So right now, I don't think there's a straight a very simple way to do so. Any drug can improve the neural networks, like okay, so the different medicines or drugs, and those drugs can improve the size of volume of the brain structure, like hippocampus. Yeah, so there are evidence of certain drugs that can affect neural network, but in terms of improving neural network, I don't, at the moment, I'm not very familiar with the pharmaceutical area of research, but I do not believe there are proven medication that can improve your brain network integrity. Um, but there are definitely cognitive enhancers, but I don't know whether those cognitive enhancers actually change the connections of your brain. So I don't know the answer to that question. So I do apologize. With age increase, physical condition may not be able to carry out aerobic training. Is there other exercise such as drawing, puzzle playing can be a way to build reserve? Yes. So I think exercise just one thing that we were looking into. And as I alluded to the earlier part of my slide, that there are different strategies that people are proposing to increase reserve capacity, including cognitive training. So what you mentioned there is actually a good example of potentially cognitive training, right? So cognitive training could be one. I do know some people are exploring music therapy, and there seems to be some promising results using music therapy. But I think currently the strongest evidence that we see is still from physical exercise. And also, I should mention brain stimulation, because brain stimulation allow us to target specific parts of the brain. And then if we want to enhance certain parts of that network or the connection of different parts of the network, I think brain stimulation will be another area, another tool that we can use to build reserve. Okay, so another question for stroke case, any difference between MRI and CT brain about the sensitivity to detect infarct or hemorrhage? CT scan and MRI, I I don't know the straight answer to this, but if you were to ask me and if I were to make an educated guess, I would probably say MRI is a better tool for identifying stroke cases because it has a much higher spatial resolution compared to CT scans. So chances are you're going to be more able to detect infarcts or hemorrhages using MRI. I think Bolton or Professor Bolton Chow also mentioned about using the combination of AI and MRI image to diagnose certain conditions. Currently, I do know there are a lot of different groups that's exploring this option using AI to help them identify stroke or other conditions on the MRI image. But for lesions that are small, like relatively small, smaller than a few voxels. So a voxel typically would be like 1 millimeter. So if for damages that's smaller than probably 3 millimeters in dimension, would be very hard for AI to detect at the moment. So right now we're still relying very much on expert radiographer and clinicians to visually check and go through different MR slices to identify these lesion locations. So my understanding is MRI is probably the better way to go because most of the clinicians I know are using MRI to detect or to identify lesions. Okay, so I think that's all for the online questions, unless there's more. And is there any more? Oh, sorry.
Sorry, the last question,
Yes.
promise. I'm interested in a question that one of the online audience
Sure.
posted about with age increase, physical condition may not be able to carry
Oh,
out
okay.
aerobic
Yes.
training. So I've come across some research before that a researcher was they were trying to evaluate people who are doing weightlifting exercises compared to another group who are thinking they are doing weightlifting exercises, but only in the head.
Yes.
It's called manifestation.
Yeah.
So have you heard about that?
Yes. So
Does it actually work?
that's a good question. And I do have a student I'm co-supervising is looking into something very similar. It's called motor imagery. So they do exactly as you said. They imagine them doing certain movements or certain exercises without actually physically engaging those activities. And what we found in the MRI is that we see very, very similar activity patterns. We see very similar activity patterns when you're imagining you're doing these activities compared to you're really doing these well, I shouldn't say you when you're really doing activity, but after you go through a period of physical training and we put them back to the MRI, we see changes in the brain activity level, and the regions do correspond really well. So I think there is some promise there for people who really can't engage in physical activity. I think motor imagery may be something that was worth looking into. But that's also in addition to things like cognitive training. Again, I think that could be very beneficial and potentially brain stimulation if the person is able to do so. All right. Any other questions before we wrap up today? I know it's getting late. I don't want to keep you guys here for too long. All right. So I think everybody is good.